All right, so at this point, we move into the discussion. So if our speakers for the session might come up front so they could use the microphone. I'll be monitoring the chat as well. So folks online, if you have questions, please go ahead and speak up. You can type your questions in the chat. Let's see. People are thinking of questions.
Mark had a question.
Oh, that's correct.
I have a question.
Here, do you want to use the mic?
Yeah. I find it quite intriguing, the whole dark matter cold and warm versus warm discussion. What can you say about the, if I would ask you what would be your favorite model right now, where would the signal of the cosmic dawn move to, and how to what frequencies, and what can you say about the strength of it? I'm just looking for, what we can expect.
Right. Yeah, so related to warm dark matter, my favorite model is probably fuzzy dark matter, as it's called, or ultralight axion. It's more technical, but fuzzy sounds funnier.
Yeah.
And it does something similar to warm dark matter in that it will cause like a turnover in the number of small halos.
Yeah.
But it does it in a modulated kind of way where there are like ripples essentially in the like number of halos. So you could actually get like these bursts of like smaller and larger halos all the way down to the smallest scales.
Yeah.
And in this model, the mass of the particle is so small that you the Broglie wavelength of dark matter is on the order of several kiloparsecs. So you actually it's kind of fascinating. So the way that it works to explain galaxy rotation curves is analogous to hydrogen atoms, where you have a potential well for the electron to sit in, and it has like several wave functions that are stable, like energy eigenvalues. And the same thing is true for these ultralight axions. Because their wavelengths are so long, they're basically caught in this dark matter, in this potential gravitational potential well, and they form like these stable waves.
Okay.
And that's kind of how you create the galaxy rotation curves that are constant all the way out.
Yeah.
And the other thing that's encouraging about axions is they're like arguably one of the only models motivated by standard model extensions. So if you demand that like dark matter must fit into the standard model, there's not a lot of like ways you can do that. And one of them is that the neutron, infamously, right, doesn't have a dipole moment and is predicted to. And one of the ways to fix that is to posit another interaction, which creates this particle called an axion. And so if axions exist, they could be the candidate for dark matter, and they could also solve this like the non-existence of the neutron dipole moment. So anyway, that's why I like ultralight dark matter so much.
But if you use those, if you use those models, can you then also predict what the effect would be on the global signal? Yeah. Can you say something about that?
Yeah. People have done a lot of that, and a lot of it will produce effects similar to like warm dark matter, in that you'll get less star formation in the smaller halos, so the signal will be shifted to later in cosmic time. Once again, that's kind of degenerate with warm dark matter models, but because it has like such a characteristic turnover in the halo mass function, you can kind of tease between the two.
Okay.
So that's like the biggest effect for the global signal. I think it should have an even more pronounced effect for the power spectrum, though.
Yeah, I was gonna. What would actually be my other question? What would you like to see, and what can you predict?
Yeah, I can't remember if I think people have done this, and it creates like really weird ripples in the K structure of the power spectrum.
What is the, let's say maybe this goes maybe too much into details. I'm just wondering about what is a spatial scale that you want to be able to see.
Oh yeah. I think it's going to be on the order of like 50 like K equals about 50 inverse megaparsecs and greater.
Okay.
Yeah.
Okay, I'll have some
roughly.
We can later. This is really fascinating. Sorry. Yeah.
So I was just going to add to what Joshua and Mark were both saying. What's I think increasingly intriguing about these 21 centimeter observations from the moon, both power spectra as well as global signal, is not only is it great to test the cosmological models for star formation models, which, we've been thinking about for years, but it increasingly is becoming a high energy physics experiment. And that's one of the reasons that the Department of Energy decided to co-fund the Lucy project, because in talking to the director of the high energy physics division at DOE, he expressed to me not too long, 6 months ago or so, he says, I'm really frustrated about dark matter. He says, we're just not making any progress from the traditional experiments in understanding this. We just get negative results and negative results. We need a new approach. And what you guys are doing may be that new approach that cracks the nut open. And so I find that fascinating as well. So we test high energy physics models, basic models of physics, as well as basic models of cosmology.
Yep, please.
Okay. For Connor, so you said that for the cold matter or the cold dark matter, that the mass is higher than for warmer dark matter. And would that imply, right, that the less matter there is, the warmer the dark matter is, and that's the signification for star formation in those zones? Because you had also talked about how stars are thought to be formed in these warmer, like dark matter pockets.
Oh yeah, so the thermal mass is essentially what the dark matter particle mass is referring to.
Okay.
Just kind of annoying units, but essentially like the greater the thermal mass, the closer it is to cold dark matter. So it's like a heavier particle. And so because of that, it tends to clump easier. And so you get a lot of smaller halos that form smaller galaxies. But if you make it warm dark matter, you're essentially decreasing the mass. And when the mass is decreased, it's easier for the particles to stream freely apart. They'll have a higher velocity. And so you don't create as many of these small halos. And so you don't get as many small galaxies,
You
essentially.
get larger galaxies.
Yeah. So it refers, specifically really to like the thermal relic mass of dark matter after decoupling from.
Okay.
Yeah.
All right, cool. Thank you.
Yeah.
I actually have a question for Neil, if you don't mind. For the Parker Solar Probe rolls that you were talking about, can you comment on how many of those have been completed? And for the ones that have been completed, I assume they're rotating around the solar axis, but that must be at an arbitrary galactic longitude where you're cutting through. So do you see differences if you're pointing towards galactic center or away, or you just get random slices, if that question makes sense?
Yeah, so I think there's about 10 of these rolls that they've done. I mean, obviously they have to do them at the portion of the orbit where they're farthest away from the sun, because they, when they're close to the sun, they can't point the heat shield away. They cook their electronics. Yeah, there are small differences because even though they point like the same angle away from the sun for each of the rolls, I think it's like 25 or 30 degrees. Yeah, obviously the orientation relative to the galaxy is slightly different, just depending on the orbit and everything. I don't see too much of a difference in the actual modulation. I think because the beam is just so large that it tends to average these things out. But yeah, I mean, I've been mostly focusing on kind of one day that appears to be the cleanest, but ultimately we want to, combine as much as possible to get these constraints to be as tight as possible. But there is just some limitations just because the beam is so large.
And how much of the data do you have to throw out from like Jovian emissions or other solar events now that it's solar maximum almost?
Yeah, so originally when I first started this, I was trying to be very precise. I was trying to throw out as little as possible. I'd create little cuts around the solar bursts. And I was actually finding that there were some residual features that weren't fit by the model. And I spent a lot of time like racking my brain about, what could this be? And basically it seemed to be something associated with the solar burst that was just kind of below what I was seeing by eye, because I was really just doing it by eye with the waterfall plots. And so now I've been more liberal about cutting more data out, and it seems to be doing a better job of leaving just the galactic signal. So for that one day that I was showing the waterfall plot of, I've been finding that really the 5 hours between like 12 and 17 hours were the best. So it's hard to, cut out that data, but also we want to get rid of any sort of low level stuff from the solar burst.
Have you asked the Parker folks if they can do an extended roll? I don't know, roll for a week. They're not doing anything else at aphelion. So
that's true. Yeah. I mean, we've been working with Mark Palupa and Stuart Bale pretty closely on this. I know Mark at one point said we could change the angle. They pointed like 25 degrees away. If we wanted to point slightly more or less, they could do that. Yeah, I don't know. We haven't asked them about doing it for a week long. I don't know if that would be feasible or not, but that's actually an interesting idea.
We have asked them about and talked with Stuart about turning off some of because there was one instrument that was added fairly late, and it looks like it did not have the same modulation of the internal noise, and that might be creating some problems. But getting back to the sun, the other thing that's really interesting about the sun, I was hoping that we might be able to tease some of this out. And talking with Stuart Bale about this recently is, is there evidence when the sun is not bursting that there's still these micro bursts that are there, and what is the level, and will that prevent us when the sun is up from doing cosmological observations? Of course, from a physics perspective of the sun, this is very interesting, and people have been speculating about this for decades. But according to what Stuart and others tell me, that really, the data has not been collected to absolutely say that this is true, because that would be fascinating with respect to understanding the heating of the corona and the magnetic field reconnection events on the sun. So anyway, we're looking for some of this and wondering, was some of this contributing to some of the noise that Neil is seeing? And I don't think so yet. I think it's just sort of other residual effects in and around, smaller type 2-3 bursts, and actually more Jupiter bursts than we recognize too. So.
Well, it would be ironic if you were looking for galactic signals and somehow solved the coronal heating problem in the process. I'm sure the solar physicists would hate you guys.
We were hoping, we're being naive about this, but we're hoping. So.
It does look like someone online has their hand up. Yeah, do you want to ask a question?
Yeah, if you have a question from online, please type it in the chat and I can read it out here.
Oh, can you guys hear me?
Oh yeah, go ahead, please ask.
Okay, yeah, I'm just going to ask directly. So this is David. This is a question for Mark. So yeah, thank you for your talk. That was very interesting to hear the plans, to combine forces between ESA and NASA. And it's just I haven't heard about that before, I believe. So I'm just curious about what you mentioned about the air matrices with antennas painted on. So what's what we would call, or with NASA would call the technical readiness level of this?
Yeah, that's a good question. Thanks, David. I think inflatable systems have a high TRL. I think it's been demonstrated on a space shuttle mission where they deployed a inflatable array or dish, a dish for I think 15 meters or something like that. And as far as I know, we were talking yesterday to someone. They said that there's inflatable structures on the space station as well. So it's kind of a habitat thing. So the thing that we are looking for is an inflatable on the moon. That is, let's say, I mean, if you want to build an array with 1,000 antennas, you need 4 air matrices, more or less, of 100 by 100 meters. So you print antennas on there across dipoles of 5 meters each. So that's the kind of size you need. That's quite big. And then you have to think about, you have to integrate the electronics as well. So you're using possibly like Kapton film on top, and you print antennas on there. And then you need to have your analog electronics close to the antennas and maybe some digital electronics in there as well. And you need to have cables and all those kind of stuff. So that's, so in principle, the answer to your question is the TRL for inflatables is high. For this purpose, there's some work is needed. But this is actually my whole point, right? I think if we can come to some kind of common design both in the US and in Europe, we could do those technology developments together. And I think that that would bring us further and help us to build a bigger array. So hope that answers your question.
Yeah, thanks. Interesting.
I think we have one more hand raised from Karan.
Yes. Hi, can you hear me?
Yes, go ahead.
Yes. So hi, this is Karan. So I'm from the gravitational wave community, and this is my first sort of hearing about the lunar and especially the astrophysics that we can do from the moon. So it's extremely inspiring to hear both the sessions, and there is so much commonality. So more than a question, I had this point of finding synergy. So we've been thinking about gravitational wave astronomy from the moon. And one of the many things, including the Voyage 2050 plan, like there's a constant effort from the gravitational wave side too, to think about, mission. Most of the sources we are interested are high redshift, beyond redshift 5, 7, the gravitational wave universe. And so I'll be really, interested in hearing what kind of synergy people are sort of interested in, possibly, if we have any sort of a joint workshop like this in the future. So yeah, this is just an open invitation to everyone on that.
Yeah, I don't know if maybe also Jack wants to comment on that, but at least what we've tried to do when we started to form the topical team within ESA, and that's now currently called the Astronomical Lunar Observatory, is we identified a couple of ideas through another ESA system where people could propose different instruments that they wanted to have on the moon. And indeed, gravitational wave detection was one of them that could be placed on the moon. So that topic is still in the list of things that could be integrated into an observatory. And this is why we call it a lunar observatory and not so much a radio telescope so far, right? So, and I think one of the questions that we had in the previous session was also, can you use it to study the moon itself, right? And in principle, we can. If we add to each of the elements that we have, it can add other instruments, and you spread it out over a large area. So yeah, there's a lot of synergies that are possible. But maybe Jack.
Yeah, I was just going to add, because we've actually talked about this a little bit before, and I've spoken to a workshop last year on gravitational observations from the moon. And I think there is a lot of synergy, both in terms of science that we could be pursuing, but also in terms of deployment strategies, large facilities, on the moon. Can we take advantage of, what we learn from our large radio telescopes and deploying large area gravitational wave detectors on the moon? So I think the answer is yes. There's also detectors, the moon is a wonderful potential detector for neutrinos and cosmic rays. So imagine ice cube on steroids, that you can do from the moon. So there's lots of those possibilities. Once we're there on the moon, and once we have the regular transportation system going, all of these things are going to be possible.
Yeah.
And we need to start thinking about these now and begin to let ourselves dream a little bit, because it's not so far off into the future.
Thank you so much for that, both the feedback. I think this is something which, for the gravitational wave community, of course, we are at a more infant stages of our astronomy in general compared to radio and other bands. But clearly the advantage of, something being demonstrated on the moon is just so far superior than what we can build in Earth for, in the coming next 2 decades. So definitely something that.
Can I add one more comment on that? I think
Sure.
one of the things that I remember from having the discussions with several teams that came with these ideas for having instruments on the moon, there was also ideas for having UV telescopes and stuff like that, and also gravitational wave detectors. I think you have to realize, do we really want to put it on the moon? Is it needed to be on the moon? And we have a gravitational wave detector in space. You can have, an even larger interferometer, right? So that would be a big advantage. So is it necessary to go to the moon? Yes or no? And I'm not sure if that's the case with gravitational waves.
Yeah, it's a yes, and I'll try to give an unbiased view on that. So we have a semantics issue here that like we don't have words like UV, radio, X-ray, etc. for gravitational wave equivalent. But the spectrum that we see from space versus the one that we see from ground, is really as far as the visible to radio telescope. And in between the band that the moon offers is something we absolutely cannot do from Earth. But even from space, I don't see for the next 20 years or 30 years, LISA is still perhaps a pathfinder to what a possible radio telescope equivalent of gravitational waves is. And this is such high frequency that we are talking about that we access on the moon, that a space mission absolutely does not have the residual acceleration to find it at this given point of time in technology. So the moon is a very natural way to reach those frequency with existing technology. Anything in space, if we want that, we are looking at definitely beyond 2050 plan for now.
Yeah, but then you see it as a piggyback mission.
Yes, I do see that as a piggyback. And that was very clear from the beginning that we don't need infrastructure as big as LIGO or Virgo to be built on the moon. We are only interested in a certain frequency band that we can achieve just by having an interferometer or seismometers on the lunar surface.
Okay, clear.
Okay, any other comments from in the room or online? No? Okay, let's thank all of our speakers again. I think that was an excellent session. Thank you very much.